the newly mapped fissure and deep magma system beneath the Campi Flegrei caldera. West of Naples, underneath one of the most densely populated stretches of coastline in Europe, sits a volcano that doesn't look like one. No towering cone, no obvious crater rim visible from a distance, just a wide, gently rolling landscape of hills, harbors, and neighborhoods, home to roughly 1.5 million people, many of them living directly inside the caldera itself without a second thought, going about ordinary mornings in cafes and apartment buildings, built across ground that has, at points in the historical record, physically risen and fallen by meters within a single human lifetime. In October of the 2025, a team of European researchers published a study revealing something new hidden beneath that landscape. A previously undetected crack-like fissure connecting the volcano's deep magma and gas reservoir directly to the surface. This is the story of what scientists just found underneath Campi Flegrei, and why it matters right now more than at almost any other point in decades. To understand why this specific discovery landed with such weight, you have to understand what Campi Flegrei actually is, because it doesn't behave like the volcanoes most people picture. Rather than a single mountain, it's a caldera, a vast, roughly circular depression formed thousands of years ago when a colossal eruption emptied out an underground magma chamber so completely that the ground above it collapsed inward. The eruption responsible for that collapse, known as the Campanian Ignimbrite, occurred approximately 39,000 years ago, and ranks among the most powerful volcanic events in Europe's history, one large enough that its ash has been found in soil layers spread across much of the Mediterranean region, from sediment cores in Russia to cave deposits studied by archaeologists investigating the era when Neanderthals and early modern humans overlapped across the European continent. Some researchers have even proposed the resulting volcanic winter and its disruption to regional ecosystems may have played some role in the broader pressures of that period, though that connection remains genuinely debated rather than settled. A second, smaller caldera-forming eruption followed roughly 15,000 years ago. Since then, the volcano has erupted dozens of smaller times, most recently in 1538, when weeks of earthquakes and ground swelling preceded the sudden birth of an entirely new hill, Monte Nuovo, in the span of about a week. A hill that still stands today, grass-covered and unremarkable looking, sitting quietly among the surrounding neighborhoods as if it had always belonged there. There's a physical monument in the town of Pozzuoli that captures just how dramatically. This ground has already moved, long before any of today's monitoring instruments existed. The ruins of an ancient Roman market known as the Serapeo still stand there, its marble columns bearing a distinct band of small holes bored by marine mollusks partway up their surface, clear physical evidence that those columns spent a period of history partially submerged in seawater before the ground beneath them rose again, lifting them back out. That single structure has become one of the clearest natural records anywhere in the world of a caldera's ground level rising and falling over centuries, long before Bradyseism was even a word volcanologists used. Since 2005, Campi Flegrei has been going through a slow, unmistakable episode of unrest that has only intensified in recent years. The ground across parts of the caldera has physically risen by roughly 1.4 meters, an effect volcanologists call Bradyseism, caused by pressure building beneath the surface as magmatic gases interact with the hydrothermal system trapped in the rock above. Earthquakes tracking that uplift have grown more frequent and more powerful, along with it culminating in a magnitude 4.6 event on June 30th, 2025. Among the strongest the area has recorded in this particular unrest cycle, an earthquake strong enough to send residents in Pozzuoli and nearby neighborhoods out into the streets in the middle of the night. As of the most recent surveillance updates in the summer of 2026, that activity hasn't stopped. Monitoring agencies logged 8 recorded earthquakes in a single week in mid-July alone, and the ground continues rising at a documented rate of roughly 10 millimeters every month, alongside geochemical readings showing a long-term trend of the underground hydrothermal system continuing to heat up. Against that backdrop of steadily building unrest, the discovery published in October 2025 mattered because it finally gave researchers a physical explanation for exactly how the underground pressure has been reaching the surface all along. A team led by Giacomo Rapignani at the University of Pisa, working alongside researchers from Italy's National Institute of Geophysics and Volcanology and Germany's GFZ Helmholtz Center for Geosciences, spent years analyzing a decade's worth of volcano-tectonic earthquakes recorded beneath the caldera. Buried inside that seismic data, they identified something nobody had clearly mapped before. Long-period seismic signals consistent with a narrow, crack-like structure sitting at a depth of roughly 3.5 kilometers, one that appears to directly connect the volcano's deeper magma and gas reservoir to the fumaroles, natural steam vents, venting near the surface at a site called Solfatara. Picture what that structure actually represents. Not a smooth, gradual seep of heat and gas working its way upward through solid rock, but something closer to a genuine plumbing line, a resonant, fluid-filled fracture acting almost like a pipe, channeling pressurized gas and heat from deep underground more directly toward the surface than researchers had previously mapped. Solfatara itself, the surface expression of that system, is a wide, otherworldly crater floor pocked with hissing steam vents and bubbling mud pools, the ground there permanently warm underfoot and faintly smelling of sulfur. A landscape tourists have walked across for centuries without necessarily realizing they were standing directly above the mouth of a structure. Scientists have only now managed to trace back down to its actual source. That kind of direct connection helps explain a pattern scientists have been watching for years. Rising ground, increasingly energetic earthquake swarms, and steadily climbing gas emissions at the surface, all now traceable, at least in part, to a specific physical conduit rather than a vaguer, poorly defined process happening somewhere beneath the caldera. There's a genuinely reassuring detail buried inside that same research, and it's important not to skip past it in the interest of drama, because leaving it out would misrepresent what the scientists themselves actually found. The resonance frequency of those long-period seismic signals, the specific acoustic signature produced by that crack-like structure, has remained stable over the multi-year period researchers studied. In practical terms, that stability indicates the rock sitting above the deeper magma, and gas reservoir has not become measurably weaker or more fractured over that stretch of time. The newly identified conduit appears to be an established, ongoing feature of how the volcano currently vents pressure, not a structure actively tearing itself open in real time. Scientists studying it have been explicit that identifying this fissure does not, on its own, signal an eruption is imminent. That caution held up again just months later when a completely separate international research team pushed even deeper, publishing new results in the spring of 2026. They produced the first detailed image of Campi Flegrei's magma system reaching all the way down to roughly 50 kilometers, deeper than anyone had previously mapped beneath the caldera. The team, combining researchers from Spain's Canary Islands Volcano Institute, Italy's National Institute of Geophysics and Volcanology, and universities in Madrid and Geneva, built their picture using a technique called receiver function analysis, essentially listening to how seismic waves generated by earthquakes on the opposite side of the planet get bent, slowed, and reshaped as they pass directly through the rock sitting beneath Campi Flegrei on their way to recording stations at the surface. Analyzing more than 5,000 of these distant teleseismic waves recorded between 2016 and 2022, researchers identified two separate zones where those seismic waves slow down noticeably, a telltale sign of partially molten rock. One sits relatively shallow, around 10 kilometers down. A compact zone researchers interpret as an active pathway funneling magma upward into the crust. The second sits far deeper, between roughly 25 and 42 kilometers down, a much thicker layer measuring some 17 kilometers in vertical extent and containing as much as 30% melt by weight, believed to represent a primitive subcrustal source feeding the entire system from below, a reservoir sitting well beneath the crust itself in the uppermost layer of the Earth's mantle. Even with that far more complete picture of the volcano's plumbing now in hand, the researchers behind the deep imaging study were careful to frame their own findings, the same way the fissure discovery had been framed months earlier. The structure they mapped, they emphasized, operates and evolves across geological timescales, not human ones, and identifying it doesn't, by itself, forecast when or whether another eruption might occur. What it does provide is something scientists have wanted for a long time: an actual physical map of the system driving Campi Flegrei's behavior, replacing decades of educated inference with genuine structural detail from the deep, primitive magma source more than 40 kilometers down, up through the shallower transfer zone, and finally through that newly identified fissure carrying heat and gas the last few kilometers to the surface. Taken together, these two discoveries, arriving within roughly 6 months of each other, have done something more significant than either could have on its own. They've replaced a patchwork of surface-level observations, tracked for 2 decades with an increasingly complete physical explanation of the machinery producing them. Scientists no longer have to describe Campi Flegrei's unrest in purely abstract terms, a vague magmatic source somewhere below, degassing in ways not fully understood. They can now point to a specific conduit at 3.5 kilometers, trace it back to a transfer zone around 10 kilometers, and follow that down to a deep, primitive magma source more than 4 times that distance below the surface. A genuine structural picture built from real, seismic data rather than theoretical modeling alone. That level of detail matters enormously for the roughly 1.5 million people living in and around the caldera today, many in the cities of Pozzuoli and parts of Naples itself, sitting directly within the boundaries of a system capable, in its geological past, of producing eruptions large enough to affect an entire continent. unlike a conical stratovolcano, where the danger zone is fairly easy to visualize radiating outward from a single peak. Campi Flegrei's hazard zone is the caldera itself, meaning a significant fraction of the people most exposed to its activity live their entire lives inside the very structure scientists are monitoring, commuting past Solfatara's steaming vents on the way to work, raising children in apartment buildings built across ground that has already visibly risen and fallen within recorded history. Improved structural understanding feeds directly into hazard modeling, helping authorities refine evacuation planning, monitoring thresholds, and the broader scientific picture of what specific warning signs, drawn from real mapped structures rather than general assumptions, would actually indicate a meaningfully changed level of risk, work that Italy's civil protection authorities have continued refining in step with each new piece of published research. So here's where that leaves things. Honestly, as of right now, Campi Flegrei remains one of the most closely monitored volcanic systems on the planet, and for good reason, given both its explosive history and its exceptionally dense modern population. The unrest that's defined the past 2 decades hasn't stopped, and by several measures, including this year's continuing ground uplift and ongoing weekly earthquake activity, it hasn't meaningfully slowed either. What has genuinely changed is how well scientists can now describe what's actually happening beneath their feet, replacing years of inference with an increasingly detailed, structurally grounded picture of the volcano's real internal plumbing. It's worth sitting with how unusual that shift actually is, scientifically speaking. For decades, monitoring a system like Campi Flegrei meant watching indirect signals from the surface, ground-level earthquake counts, gas chemistry, and working backward to guess at what might be happening far below, the way a doctor might infer something about an internal organ purely from a patient's pulse and temperature without ever being able to see it directly. What changed across these 2 studies, arriving within months of each other in 2025 and 2026, is that scientists effectively gained the equivalent of a full body scan, tracing the system from a specific fissure just a few kilometers down through an intermediate transfer zone, all the way to a primitive magma source buried deep in the upper mantle. That's not a minor technical footnote. It's the difference between describing symptoms and finally being able to point to the actual anatomy producing them. Neither of the newly published discoveries, the shallow fissure or the deep magma system beneath it, points to an imminent eruption. Researchers behind both studies have said so explicitly in their own words more than once. What they do confirm is that Campi Flegrei is, and has been for 2 decades, an actively evolving system, one that just became considerably better mapped than it has ever been before, and one that scientists across 3 countries are now watching with a level of structural detail nobody studying this caldera has ever had access to until now, following that pressure all the way from a molten reservoir in the upper mantle, up through kilometers of solid rock, out through a single resonant fracture and into the warm, sulfur-scented air still rising over Solfatara today.